From previous introduction, we understand that Taguchi method is based on the linear additive model from the fractional factorial experiment. We can establish a linear additive model from our fractional factorial experiment, which is orthogonal array design. So we can use the model to predict any combination in the full factorial. Therefore, we can use the response table or the effect plot to predict what will be the best output, what will be the best combination to have the maximum SN ratio. So we can use this property to verify that whether our verified result satisfy this kind of assumption. I'm using this cantilever bin again as an example. In that spring example, we want to design a cantilever spring with k equal to 1, and this is the initial design. So from the parameter design, we can get the optimum design, where the optimum design after two-stage optimization is showing over here. And this is the initial design. So we can use outer array experiment to verify what is the actual SN ratio. For initial design is 25.44, and for the optimum design is 26.69. How about from the linear additive model? Since we claim that we can use the linear additive model to predict any combination in the full factorial. That is the reason why we can use fractional factorial and use the result analysis mean to predict what will be the best parameter design. So from the response table over here, we can get the main effect for all the control factors. And the linear additive model can be written as this equation. For the main effects, BHLE is shown over here. This is the main effect for BHLE at level 1, level 2, level 3. You can use the simple equation we introduced in the previous section, that by subtract the mean average from the average output of each level, we can get the corresponding main effect. If you look at the effect plot, this is the effect plot for these control factors. And this green line stands for the average mu. So the main effect for each control factors will be the difference between the average output, which is the result from the response table, and the average mean. So in this case, this will be H3, which is the main effect of H when it is set at level 3. So using this additive model, you can predict any combination by just substitute IJKL into this model and substitute the corresponding main effect value. You can predict the SN ratio. Let's use this model to predict the SN ratio for the initial design and also the SN ratio for the optimum design, and to compare whether that improvement is the same as the result from the outer array experiments. This is a two-stage optimization, which is a nominal the best problem. So we have a scaling factor, which is L in this case. And L is a type 3 control factors. Therefore, type 3 control factors has little or no effect on SN ratio. Especially when we do the two-stage optimization, the scaling factor will not be at any preset level. So we cannot find the corresponding main effect for these scaling factors. In order to compare the improvement between the initial design and optimum design, usually we will neglect the scaling factors in a comparison by only using the rest of the control factors. As you can see here, the main effect of L is neglected, since L is the scaling factors, which will not be set at any specific level. From the initial design, the level is 2, 2, 2, 1, so you substitute this combination into the additive model, you will get the prediction should be mu plus B2, H2, and E1, and the corresponding result will be 25.42. Similarly, you can estimate what will be the SN ratio for the optimum design, which is 331. This question mark stands for the scaling factors, which is not at any specific level. So we neglect the effect of L and come up the optimum design will have 26.59 SN ratio from the linear adaptive model. We can put the estimated result from the linear adaptive model and the verified result from the outer array. For the robust and the initial design and also the gain. The gain is the difference of the SN ratio between the robust design and the initial design. So from the linear adaptive models, we estimate the improvement will be 1.17 dB. From the experiment, where you can see the data over here, and put them into the tables, and you will get the actual gain is 1.25. From this verification table, you can understand that both the predictions of the SN ratio for both design are very similar to the exact value. Certainly, the gain is very similar too. Among three of them, the gain is the most important number, since this is the actual improvement we really care. The verification is 1.25, the prediction is 1.17. They are pretty close. So we can conclude that your experiment is successful, and also your design of experiment is based on the reasonable assumption. And this linear adaptive model is satisfied as a predicting model. However, how do you conclude whether the difference is small enough in order to conclude your design of experiment is a valid design? Here we propose a rule of thumb to have a first cut about your experimental result. So once you have the experiment, and you can compare mainly the gain. Compare the predicted gain, delta, and the verified gain. If the verified gain is within plus and 50% of the predicted gain, we assume your experimental result is successful, and your optimum parameters is verified. However, if your verified result is outside 50% of the predicted result, we will say that your adaptive model failed to estimate the SN ratio of the factorial experiment. So you need to redo the design of experiment. So first, when you get the verified result, you can compare your optimal SN ratio with the rest of the design samples. If it is larger than the current samples, that is the first step. And then you use this verification table and to make sure that the verified result is within the 50% plus and minus this range of the prediction result, and you can conclude your experiment is successful. And your robust parameter design is a good selection. So we conclude the result to be 4 cases. This is your estimated result from the adaptive model. And if you conduct the outer array experiment, and you put the result over here. For the first case, if you have the data like this, the number showing in the table, you can see both the prediction of the design, initial, robust, are very similar. Also, the gain is very similar. There are only limited differences. We can conclude that you have a strong confirmation of your design of experiment because you have good estimation for the gain. What if for the second case, if your data looks like this way? If I look at the gain is about 20 dB, which is still very close to the predicted gain. But when you look at the verified data of the SN ratio for both robust and initial design, you will find out there's a slightly larger difference. The predictions is 33.4, but the actual value is 29. It is bigger than the previous case. However, if you look at that, you can understand there is a static difference between your verified result for both robust and initial design. You have a static error. So you can conclude that you have a weak confirmation of your result. Why still a confirmation? Because your gain is similar to the predicted value. But there's a static difference between the predicting value of robust design and initial design. So there might be some significant factors which are missing in your model. So you need to go back to your experiment and go back to your model to examine whether there is some important control factors you didn't include into your model. However, for the current control factors, your selection for the robust optimum is still a valid selection. What if this is your verified result? As I mentioned, we use the 50% of the predicting gain to be the range. If our verified result is within 50% of the predicting gain, then we will conclude this is a good confirmation. For the estimated result is 20, about 20. So between plus and minus 50%, the reasonable range for the verified result should be within 10 to 30. In this case, when you look at the gain, again, look at the gain first, you find out that your verified gain is greater than 30, which is outside the range of the reasonable prediction. If you further examine the data for both robust design and initial design, you can see there are a big difference. So if you look at the design of an experiment, you have a bad confirmation, since this is outside the 50% range. What is the possible reason? First, interactions. There might be some factors which have interactions, and you cannot determine the best combination for each factor independently. How to resolve this situation, we will talk about that in the following section. However, let's go back to what's the purpose of your experiment. Your purpose is to find a better design which have a larger SN ratio. So look at the result you have. What is your result? Your robust design has a very good SN ratio, which is even bigger than the prediction. So in terms of the design purpose, you are successful since you do find a robust design which is much better than the initial design. However, the result cannot be predicted from the linear adaptive model, which means that the linear adaptive model is not sufficient. You should include some other effects such as the interaction effects or maybe some other control factors effects into your model in order to get a good prediction. But no matter what, you solve the problem. You do find a good design. But how do you do that? You don't know. You're just lucky. So in terms of the real application, the optimum combination is still okay. You can use in your future design to get a better SN ratio. But if you want to establish a better model for future predictions, you might need to include the interaction into your linear model. This is case 4. While we mentioned this should be between, a reasonable prediction should be between 10 to 30s. Case 3 is in the higher end, greater than 30. But in case 4, your result is less than 10. Then you really run into trouble. Not just you have a bad confirmation of your design of experiment, and the possible reason is still the same, interaction, and possible missing some other important control factors. And the most important thing is you didn't solve the problem. You didn't find a better design, Although you might claim that, well, this is still a better design. There are some improvement. But for the case 4, there is a great chance that if you compare your so-called robust design with your current design of experiment samples, you might find out some other design has a better performance than your so-called robust design. That is the reason why we say that under this circumstance, your design of experiment will fail in this case. What do? Then you need to redesign your experiment and carefully examine all the possible factors and interactions in order to get a better prediction. Let's go back to look at the like I played example and use the linear adaptive model to verify whether our previous optimum design prediction is correct. Let's get some recall from this slide. We want to reduce the replication error for the V-cut feature, and this is the size and dimension of the V-cut. And we consider both the angle, the leading angle, and also the height of the feature. By consider 6 control factors. So we conduct an L18 experiment, and from the analysis of mean, we conclude this is our optimum design. Because this is a smaller the better problem, we don't need to go through 2-stage optimization. We simply pick up those levels where provide the maximum SN ratio and predict this combination will give us the best SN ratio in the full factorial. And we put that into experiment, and this is our verified SN ratio result. Let's just look at the height of the feature. The result is 7.06. In the previous case, we simply compare this 7.06 with the current 18 samples. And we were glad to find out that this design has the largest SN ratio comparing with the current 18 samples. Kind of happy that we solved the problem. But is this design of experiment can be verified? Is this design really the best in the full factorial? So let's establish the linear adaptive model and using verification table to examine the data. This is the adaptive model for this LGP example. We have 6 control factors, and this is the mean value. So the linear adaptive model is showing over here. This is the effect plot for this example. So you can see that this green circle represents the best combination where we have the largest SN ratio. Certainly that the E is a trade-off between the angle and the height, so we settle with E3 rather than E2. From this experiment, you can substitute all the main effects. And the main effects is the difference between the average output and the mean. So this is A1, this is A2, and this is A3. Do the same thing for the rest of the factors. You can come up the main effect table. You can predict any combinations. So that's the reason we assume once we select these optimum selections, we might have a largest SN, since each factor at this level will give us the largest main effect. By substitute these selections into the model, you can get the predictions. The optimum design is 1, 1, 1, 2, 3, 1. This is the parameter design. And so we can select the corresponding main effect, which I marked with the red letters, and plus the total average. The prediction for the optimum parameter design is 11.9, which should be the SN ratio. Let's go back to look at the data. What is the data from the experiment? Well, 7.06. Certainly, this is still okay result. Using the rule of thumb, we use 50% of the predicted output as a checking mark. Here we don't have an initial design to compare, so we didn't compare again. Let's look at the value, the prediction value directly. The predicted value is 11.9. Let's make it 12 for easy calculation. So 50% will be 6. Therefore, if the verified result is between 6 to 18, you are okay. How about in this case? The verified result is 7.06. Well, it is okay. But as you can see, this is very close to the lower bound, and which is on the bad direction. Since if it provides a better result than prediction, we will be happy. But this is close to the lower bound. It is currently 7.06. Okay, but you might have a feeling that you are not that sure whether this combination will be the best in the full factorial. But you still solve the problem since you get the improved design. So what will be the reason why this is not as good as what we predicted? As we mentioned before, there still be possible interaction effect in your model. But the interaction effect may be not that significant to affect your selection. But you still need to be careful if you want to further improve your design by doing the second round of design of experiment.